Thank you so much to everyone, both virtually online and here in person, for coming along to support this workshop. I hope you get a lot out of it. I'm Barry Cooper from the University of Exeter, working on a project with Gihan Marasinghe and Tara Fujita, looking at the effectiveness of lean in teaching mathematics. And it strikes me that we're in quite an exciting period for interactive theorem provers. They've been around for a long time. And if I might make the analogy with simulations and programming and computing power over the last century, perhaps, and the way that for a long time that was quite a niche activity, it took a while for that to become accepted as something that it is worth teaching undergraduate mathematicians. And now it would be unthinkable that we wouldn't have some form of programming course within our mathematics degree programs. I wonder if, and I hope that maybe, who knows, the next decade, give or take, that might become true of interacting theorem proving for the theorem proving community. So I find this a really exciting time, and I'm really excited to hear about all the progress that's being made in education and research with interactive theorem provers. And thank you so much in advance to all our contributors to the day. So without further ado, I'm going to hand over to Athina Thoma, who is presenting from online, who's going to give us our first talk on learning lean, exploring students' perspectives and use of lean. And Athina, you've got 25 minutes, half an hour, and at 12:30, we'll go straight into Patrick's talk, and we'll save questions if we can until 12 o'clock. Thank you so much, Athina.
Wonderful. Thank you very much, Barry. I can see that you can see my screen, so hopefully that's okay. I completely agree with you, Barry, in terms of the excitement at this particular kind of age that we're in, where we see that interactive theorem provers are becoming much more prevalent also in mathematics undergraduate degrees. So I will share with you today a few studies that my colleague Paola Iannone from University of Edinburgh and myself have engaged in. And these studies are looking into how mathematics undergraduate students are engaging with lean. And I'll take you through essentially 3 different studies that we have kind of looked at different aspects. So I'll just do a very brief introduction to studies in mathematics education on proof and research on programming in the mathematics education community. And then I'll share with you some studies reporting on students' perspectives and use of lean. Within the mathematics education community, proof has always been a major topic of a study because of the role that it plays in university mathematics education, but also in terms of the difficulties that the students are facing when they are engaging with kind of learning how to prove, or what is kind of the acceptable way of writing a proof, structuring a proof, and so on. So I've listed here for you on the slide a few studies that have looked into how students perceive that the role of the proof is, or, for example, studies that are looking into how students write about proof and what are the difficulties that they have with the writing. So, for example, they're not defining the mathematical objects very clearly. They provide strings of symbols, of mathematical symbols that don't necessarily have a clear kind of connection between them. They provide statements that are not logically connected with the ones before or the ones after. And there are studies also that have looked into when students are presented with a proof or proofs, how do they actually check their validity? There are studies comparing what students are doing with what their lecturers are doing, and we see that there are huge differences between how, let's say, experts in mathematics are writing proofs and are looking at validating proofs and so on, compared to how students approach this, especially if they're first-year students, when they are kind of initially being introduced to the practices of proof writing. And also very nicely linked to what you were saying earlier, Barry, in terms of how programming is much more prevalent now into mathematics degrees and how we see a lot more links. we see that in mathematics education community, we see that there are a lot of modules within mathematics departments that are using, that have programming. However, within the mathematics education community, we have not essentially yet conducted enough studies to explore how there are potential links between, let's say, students' learning of mathematics at university level and students' learning and using of programming. So kind of interactive theory improvers fit somewhere in the middle of kind of programming and mathematics at the same time. And this is why I was very interested in kind of getting involved in this type of projects and seeing what's happening when students are using Lean. So I'm sure we'll hear more from kind of Abigail and other colleagues later on as well in the day. But we have one of the first studies that was looking into how students kind of engaged with Lean is Abigad's in 2019, where he essentially talks about a course that he delivers with a few undergraduate students, and there they discuss the different kind of languages that are at play. We have the mathematics language, we have the Lean language, and the students are essentially moving between those two, and they're talking about kind of the differences in engaging with this. And we also have a study by Gila, Hannah, and her colleagues who are discussing the role that interactive theory improvers could play in fostering the appreciation of students regarding proof, and also the way that students understand proof. However, in their study, Gila, Hannah, and her colleagues, they were mainly focusing on kind of analyzing the theory improvers, but without actually collecting data from students themselves at that point when they wrote this particular article. So in our studies with Paula, we focus on collecting data from students who are using Lean, and we want to see what are the different kind of impacts that using Lean might have on the way that, for example, they're writing proofs. So this leads me to the first study that I will share with you. And this study took place in a first-year foundation of analysis module, where students were looking at number systems. They were looking at induction, binomial theorem, equivalence relations, and different and other topics as well. There were optional Lean sessions on Thursday evenings. It wasn't a compulsory part to engage in Lean. And some information about Lean was also given in the lecture. So the lecturer who was delivering this module was also showcasing at different points during his lectures aspects of Lean code within the lecture. The aim that we have in that project was to look at the potential impact that Lean might have on the way that students write pen and paper proof. And we wanted to see whether there were particular characteristics that were prevalent in students' proofs when they were Lean users compared to the ones that were not Lean users. So we gave them a task that was unfamiliar to them on purpose. So they had not seen in their module the idea of abundant numbers. Some of them were familiar with the idea of perfect numbers, but not all of them. But none of them were familiar with the idea of abundant numbers. And what we did was we interviewed students who engaged in this task. We asked them to prove this task. And while they were proving it, we were also recording what they were thinking. So they were sharing with us why they were doing the things that they were doing in terms of writing their proof. And we drew from educational studies, and we looked at the proofs of the students by separating them initially using Selden and Selden's framework to the formal rhetorical part of the proof, so the part of where the students were discussing the definition of the proof and the statement that they had to prove, but they didn't actually start the proof yet. And the problem-centered part, where the students were actually starting to engage with the definition of the abundant number, the perfect number, trying to kind of logically connect their statements. And then we used Fukara and Connolly's list of students' actions to analyze in much more detail the responses of the students. So for example, we looked at whether the statements that they provided were logically connected, whether they were using examples or not in their proof, whether their proof was structured in a particular way, and so on. So we also asked a mathematician who was not familiar with the students or the task itself, because we wanted somebody who was completely neutral to the project, because Paula and I were aware of the students, and also we didn't want to be biased towards kind of marking the proofs of the students. So we asked an independent mathematician to kind of mark the proofs of the students, and we asked him to score these from 0 to 4. 0 being a proof that hasn't essentially kind of done any progress towards providing a complete proof of the statement, and 4 being a proof that would score the highest and is complete. And you can see on that slide the breakdown of the 36 students. And what we did then, we looked at students who scored the same score from lean users and non-lean users. And we looked in more detail into those responses, because in the eyes of the independent assessor, those scripts would have received the same score. So we wanted to see whether there were any differences in the way that the students were writing, if they were lean users or non-lean users. So, of course, all the students engaged with the new definitions, the definition of perfect number and abundant numbers, but we see that the lean users were much more specific in terms of the limit cases for K. So, for example, they were much more vocal, and they were writing it also on their scripts regarding the values of 0 and 1, what would happen if that was the case. And also they rewrote the definition of perfect and abundant number rather than just discussed it. In terms of the structure and the rigor, we saw that the lean users had much more structured proofs. They were naming the lemmas that they were using, and then were linking these. They were also containing full sentences, and they were discussing the relationships between the mathematical objects much more explicitly. Also, we saw that they were using much more quantifiers and symbols compared to the non-lean users. In terms, though, of examples, we see that the lean users did not actually rely on working with examples. And in one case, this particularly led to the student not completing the proof, and actually being quite agitated with himself for not completing the proof, because they got so much into trying to formalize what they wanted, and they were not able to see the idea or move between the formalization and checking with some examples, for example. And this aspect was not, with the example that I just shared with you, was not always helpful in terms of proceeding with the proof production. It was also interesting to see that the students who actually provided those, the lean proofs, the lean users, were saying that this would be an acceptable proof by lean, or, for example, this section of my proof, lean is not going to be happy with me if I wrote this in lean code, for example. But from the previous table that I shared with you, you might have seen that we didn't have a lot of students who actually engaged with lean. So we wanted to see why that was the case, and to kind of gain information regarding that, we did questionnaires with a whole cohort, and we also relied on the interviews we had with the 36 students. And we wanted to find out what were the difficulties that the students encountered when they were using lean in this particular module, and also whether their engagement with lean actually changed the way that they viewed mathematics. So We looked at questionnaire responses from 99 students and the 37 interviews where students were asked further kind of questions in terms of their engagement with Lean. And to kind of analyze that data, we looked into computer science education research articles, and we found an article by Kian and Lehman, who discussed the difficulties that computer science students have. And they essentially discussed the difficulties of the students regarding syntactic difficulties, conceptual difficulties, and strategic difficulties. When we looked at our data, we also organized our data according to these categories, but we also found out further categories in terms of, for example, how students were speaking, whether they liked or they didn't like Lean, whether they were finding it interesting or not. So we found that a lot of students had difficulties with the syntactic knowledge, and they shared that there were a lot of time constraints in terms of engaging with Lean. Some students actually discussed how the experience with Lean changed their perceptions of mathematics, how they started seeing how mathematics is kind of built. As I shared earlier briefly, the majority of the students did not actually engage due to the difficult syntax and also the perception that coding in Lean is not actually helpful or beneficial in terms of their proving strategies and their proving techniques. So we're now going to a different study where we're now interested in seeing when students are actually proving in Lean, what happens. So I'll take you through the context first, and then I'll provide you a bit more information. So this is a different year one module where the students are kind of focusing again on logic, set functions, sequences, groups, column vectors, vector spaces. So they have a variety of topics that they see. It's a whole year-long module. And they had hourly lectures and weekly seminar classes. But again, the weekly seminar classes in Lean were not a compulsory part. So the students did not have to engage. And these were on Monday mornings this time for this particular module. We did different kind of data collection methods. So we collected information through questionnaires and interviews. But what I will discuss here with you today is interviews that we had with 4 students who were very keen, and they were being interviewed throughout the whole summer, essentially, and they played the natural number game, which, Gihan, am I right in thinking that you used it this morning? Yes, wonderful. I can see your head nodding. Thank you. So the students were asked to go through the natural number game levels, and they were sharing their screen with us, and we asked them to share with us what they did and what they were thinking as they were going through the different levels. And our particular aim this time was to think about what are the students' activities when they're actually writing Lean proofs in the natural number game. So although you've seen the natural number game in a few slides, I will briefly go through it, but as you've actually played with it already, I'm going to go through those slides a bit faster. So when we're thinking about students' activity when using a particular learning resource like the natural number game, we wanted to find a framework that would allow us to understand what the students are doing and how they're using Lean. So what we did is we used a framework called instrumental approach that is based on, for example, activity theory and the theory of conceptual fields. The idea is that within this framework, the researchers are able to explore goal-directed instrumented activity. So we looked at artifacts. In our case, the artifact is the natural number game. And schemes, ways that the students' activity is organized when they're actually using the natural number game and learning Lean. So while kind of trying to prove a proof in Lean, we wanted to see how the activity of the students is shaped by the artifact, in our case, Lean. So there are particular aspects that we're looking into through this framework. We're looking at the goals of the activity of the students, so what they have to prove at each particular level. The rules of action, so rules that govern their activity. What do they do? Do they go and look at the previous coding that they've written, for example? Do they look at the error messages that they receive from Lean? So what are they doing when they're writing the proof? But also thinking at kind of the knowledge that they have and that is helping them to base what they're going to be doing next. And also this whole organization of activities constantly changing and developing. So where we see essentially students kind of learning while they are using Lean. So we were looking, we wanted to see students' activity when they were proving the same level and to see how they essentially, how did they structure the proof and what kind of actions they used when they were proving. But also we wanted to see what kind of development we see when we're looking at one student's activity throughout multiple tasks. So extremely briefly, Gihan, can I just get a nod? Did you see the natural number game in Lean 4 or Lean 3? 4, wonderful. So this is the natural number game that the students engaged in our study was based on Lean 3. So it's a slightly different kind of context to what you have already engaged. So they have similar kind of structure to what you've seen in Lean 4. So you have different worlds that you are visiting and you're asked to prove different statements, and as you're proving them, you move and proceed to the kind of the next level, and you can use the statements that you've proven. And this is the layout of what the students were seeing. In the green box, they were writing their code, and then on the right-hand side, they were able to see the goals and that they had to prove in the context, but also warnings if they had any error messages. And on the left-hand side of the screen, they slowly collected the different tactics and theorem statements that they could use. So one of the levels, I'm not sure whether you've reached the advanced proposition world when you were playing earlier, but if not, you might want to give it a go after you see what these two students did. So in one of the levels, level 4 in the advanced proposition world, the students were asked to prove this statement. And if we look at the different proofs that they produced, we see that Gemma's proof on the left-hand side is much longer compared to Matt's proof, which is much shorter. Matt is using much more efficient symbolism by naming the hypothesis, for example, with H1 and H2, using tactics that allow him to do multiple things within one tactic. And also he's using the repeat tactic to essentially close multiple goals sooner. Whereas Gemma is kind of writing much more detailed, she's writing a much more detailed code. When we were asking the students and we were essentially looking at what they were doing and what they were saying, we saw that Gemma specifically wanted her proof to look as similar as possible to her pen and paper proof. She didn't want to cheat, as for example, she called it, so use a tactic that would close multiple goals. Whereas Matt was really fascinated by this aspect of Lean and was really keen on doing that. So we call these kind of two different schemes. So Gemma is using kind of the verify step-by-step, so writing a code and checking what to do next and how to kind of structure the next part of the proof. Whereas we see that Matt is doing kind of is using tactics that allow him to close multiple goals within one line of code. And we see that these particular ways of activity were based on their preference in terms of how they wanted their proofs to kind of to look like. Now, if we move to two different students, I want to show you very briefly what they did. So if we look at the level 6 of addition world, and this is again is in the natural number game Lean 3, we see that Ben and Josh wrote, I would say, similar proof in this particular level. But you'll see on the right-hand side of the proofs, I've noted down some numbers. So the numbers indicate whether the student changed the line of code multiple times or not before it being part of the final proof. So for example, Ben attempted 7 different lines of code before actually deciding to do rewrite, add a sock. Whereas Josh was able to essentially have a much more linear production of code. So let's look at these in kind of in more detail in terms of what the students said and what the students did. So Ben was attempting quite a few things, and he said that he was kind of trying things without really knowing why he was doing this and what was kind of what would Lean give him as a result. And because the cost of the mistake is nothing, I really like this phrase that he said, it's like programming. So I can write something and I can immediately get feedback. So he liked that aspect, and not having a clear idea of what to do was not necessarily a problem for him. When we look at Josh's activity, we see that before starting his proof, he really engaged with information that was provided in the level. He carefully considered the constraints of the brackets not being visible in the context and the goals of the proof, and also considered the different available theorem statements that he had on the left panel. After completing his proof, he also went into the proof code and wrote different things to try to see what that line of code would do. So we have a slightly different way of engaging. I know that Gihan, you told me 28. Barry said 25 minutes. So I'll just very briefly go for 1 more minute, if that's okay. Level 9, we see now that both Ben and Josh have very different proofs written. Josh essentially uses the induction tactic to prove this statement. And we see now that Ben has a plan from the beginning in terms of how he wanted to structure his code, but also he's much more aware of what the different tactics do. And as you see from his statement, this is about a month into our interview. So he engaged in Lean through the natural number game quite a lot. And he's able to make some tactics much more specific by inserting variables within the code. In terms of what Josh did, it's again similar to what he had done in the previous level, reflecting on the proof, create a plan, and only starts writing code once he's satisfied with that plan. He uses the brackets to create a clear structure and uses sorry when he wanted to essentially kind of leave a gap there and then continue with the structure aspect of his proof. And he has very clear expectations of how Lean should react when he inputs a particular line of code. And again, as before, he considers alterations of his code when he is kind of finishing. So to kind of close, we see that we have a different, that the two students actually followed a different path in the natural number game. So you saw that this tree appears at the beginning and the students can choose from the addition world to either go down to the multiplication world or the function world. It's up to them. And Ben chose to go to multiplication world much later compared to Josh. However, Josh had a very clear idea of how he was going to engage with these proofs from the beginning. So we see that the way that they essentially proved these statements and the way that they engaged with the natural number game had an impact on how long they needed to complete the levels, but also how many attempts they had to do before actually finding the line of code that actually stayed in the proof. So we have quite a lot more data from those students, and we're now looking into further details regarding how this development of the activities has taken place in terms of engaging with Lean. And I want to say a huge thank you to our collaborators and also to Paula. And I think I saw Kevin and Gihan in the room, so hello from me as well.
That's wonderful. Thank you so much, Athena, and beautifully to time as well. We'll save questions and discussion for later. Do use the Q&A tab in the chat if you want to put your questions in now. I'm going to ask Patrick if you might share your screen and just check that everything works before I introduce you.
Yes, let's try to do that.
Lovely, we can certainly hear you. Yeah, your screen is coming up.
Do you see anything?
We do, yeah, we can see your screen. So it's our great pleasure to introduce Patrick Massot, who's going to talk to us for 28 minutes, apparently, on teaching using a proof assistant and controlled natural language. Thank you, Patrick.
Okay, thanks. No, thanks for the invitation. I'm sorry I'm not physically in Exeter, but it's nice to talk to you. So this talk will mostly be an interactive demo of a teaching library I've been working on for some time. So I just pasted in the Zoom chat the link to this GitHub repository. If you want to follow along, you can, if you know how to use Lean on your computer, you know what to do. Otherwise, you can try clicking this open in Gitpod project, and after a while, you'll be ready to follow me. And so you can do that right now. But while you are loading the repository, if you want, I will give you some context about this. So this is all about teaching mathematics using a proof assistant. So not teaching using the proof assistant as a goal. So the goal is to teach students how to write mathematics on paper, traditional pen and paper mathematics. And the computer is an intermediate tool in this teaching. This is what I'm talking about today. This is not the only thing you can do with a proof assistant, obviously. And I've been also teaching courses where the proof assistant is the main goal, but this is not what my talk today is about. So I've been teaching mathematics using Lean since January 2019, I think, in Orsay, at University Paris-Saclay. And but the version of the library that I will show today has evolved since in the past 5 years, and especially the Lean 4 version that I will be showing today has been written in at CMU, actually, not in Orsay, at the Hoskinson Center for Formal Mathematics. And you can read a lot more about this in a paper that you can find in the repository too. If you click this link, you'll get the paper that I wrote for ITP about this. So the context again is teaching first-year undergrad students, and I teach them in the second term, in the spring term. So during the fall term, their first term at university, they learn about calculus with epsilon and deltas, but they see proofs during lectures, but they don't really do proofs, abstract proofs themselves. So when they come to my course, we start again and explain all this proof thing, and we don't introduce any new mathematics. We just redo things that they did in the previous term, but this time really thinking about the proof. And I say we because originally I was teaching this alone, but then I got reinforcement from Frédéric Bourgeois and Christine Paulin-Morin in more recent years. So the main pedagogical goals are, so first having a very, very clear idea about what is the current state of the proof. So when students are proving something about sequences of real numbers or functions, continuous functions from real numbers to real numbers, which are the main objects, I want them to have a crystal clear opinion about what is currently fixed, what are the current assumptions, what is the current goal. So that's the first thing, not being confused about where we are. and then having a very clear distinction between stating something, proving something, or using something. And the funny thing is, you may think that every mathematics teacher has this goal of having a clear distinction between stating, proving, and using, but one clear indication that it's not so true is that in mathematics, we don't have words for that. I mean, I'm using stating, proving, and using, but the people in mathematical logic and computer science, they have more precise names like introduction rules or elimination rules, and that prove that they are more explicit about this. If we don't have a name for something, we are not really teaching it explicitly. So I want to be clear about that, and also, especially in this context of analysis, being clear about what is a bound variable and what is a free variable. So bound variable means it's something that is hidden under a quantifier. A free variable means it's free to refer to the something that has been introduced earlier. And less important goals are working on the distinction between safe steps and unsafe steps. Like if the goal starts with for all positive epsilon, then starting the proof with let's fix a positive epsilon is a safe step. And there is nothing can go wrong if you do that. Whereas if you need to instantiate an existential quantifier, for instance, then you need to commit and be brave and announce this will work and this is unsafe. And so working on this distinction is also a goal, and of course also thinking about the less direct strategies. So all those were already my goals 5 years ago, and then what happened is that I started using Lean in the traditional way, using traditional tactics, and and surprisingly, it worked pretty well. I mean, students were not scared by the syntax. They were able to write proofs using Lean, but then I was pretty disappointed by the skill transfer to paper. So they had a hard time transferring those proof skills to traditional pen and paper mathematics. So let's see, I think 4 or 5 versions of the same proof. So here is an example. You've got a continuous function f, a function that is continuous at some real number x0. So this is what it says here. F is a function from real number to real number. U is a sequence of real numbers. X0 is a real number. Next line say f is continuous at x0 and u tends to x0. And the goal is to prove that the composite sequence f compose u goes to f of x0. Maybe I should ask for people who are in the room at Exceler whether this is large enough on screen, or should I increase the font size? I think I see a tiny thumb up. Yeah, okay. So first style that I would never dare using, but for instance, Frédéric Tranmin in Grenoble uses proof terms. So you can prove this lemma using this proof term. So this is written on three lines for clarity, but this is really one huge line. I mean, I could put everything on the same line, and Lean is happy, and somehow this is interesting if you're into mathematical logic or type theory, but I would not recommend asking students to do that. I tried on some CMU students just on the side last year, and the result was what I expected. And this is really hard to write directly. And then, so I'm just writing this for completeness, but let's move to what I did in 2019 was using the traditional Lean tactics. So you can see the nice thing about this is the tactic state. So this is really the main point. The Lean tells you, I kind of assume everybody is at least vaguely familiar with what it looks like to use a proof assistant, but very quickly, the main thing is that after introducing this epsilon and an assumption that I named epsilon pos, you've got your new context. The context went from this f compose u converges to fx0. Oh yeah, there is notation that is kicking. I guess it was Yeah, okay. So the F compose U converges to F x0 is notation for sequence tends to F compose U F of x0. And then the state is updated, and we've got epsilon that is fixed, and an assumption epsilon post saying that epsilon is positive, and you move on, and this sequence of tactic is building exactly the same proof as the direct proof term that I gave earlier. So, but again, this worked surprisingly well. This worked on good students, not elite students, but good students who were enrolled in a double major in mathematics and computer science. So they had programming courses, but not functional programming, but they had introduction to programming in parallel, and they did not fear computers, and it worked well on the computer, but then the paper result was not as good as I hoped for. And so after 2 years doing that, I switched to control natural language. So this is the next version, so starting on this line 29. So the exact same proof, but using a different tactic language. So first, the statement is slightly different. So there is this keyword exercise, it has a title, and the data and the assumption and the conclusions are more clearly distinguished than in the normal syntax of Lean. If you compare with the previous example, everything is with parentheses and just in succession, and you need to spot, for instance, that this column is separating the assumption from the conclusion, and so I mean little clarity improvement with this. And then, but then the main thing is that those tactics now read like natural language. So maybe slightly rigid or maybe very rigid natural language, but still, if you read that, it's much easier to write a proof on paper. And hopefully, after having written that sufficiently often, then you can write such a proof on paper directly without needing the computer as an intermediate tool. Okay, so this is still Lean code, so this is still extremely rigid. If you have a typo, so if I delete this I, then everything becomes red, and there are errors, and yeah, unsolved goal, unexpected identifiers. It's a mess. So it's really completely rigid syntax, but it sounds like mathematical natural language. And now there are many variations. So this library that I'm using that define those tactics. So this is the verbose Lean library. So if you want to use it, by the way, what does it look like? You create a project, and simply inside the leg file.toml, there is this require verbose with the git URL. So the 3 lines that tell I will use this teaching library are those lines. Okay. So this library defines all those tactics. Let's prove that, fix, and buy, and stuff like this. But there are many different styles that are available in this library. So let's see a different style. Because the first version that we saw is still in spirit very close to the normal tactic language of Lean. So let's see something that would be closer to what we write on paper by not giving names or not using names of assumption. So the first 2 lines are the same, but in the third line, instead of saying by HF applied to epsilon, so where HF is the name of the continuity assumption, you say since f is continuous at x0 and epsilon is positive, we get delta such that, and then it's the same thing. So you see, it refers to the fact that f is continuous at x0 without using the name of this fact, and it also refers to the fact that epsilon is positive without specifying that we will specialize this continuity assumption to epsilon. If you compare to here, it's applied to epsilon using that epsilon is positive. Is a bit cluttered, and on paper we would have such a shortcut since f is continuous and epsilon is positive, we get delta. And notice, by the way, regarding this pedagogical goal, that we should distinguish clearly stating something and using something, that when I write we get delta, I do not write there exists delta. Because if I write there exists delta, then I'm only claiming the existence of delta, but not fixing one delta that works. So we could say, since f is continuous at x0 and epsilon is positive, there exists delta such that, and then let's fix such a delta, but that would be a bit heavy. And so this we get delta is my trick to clearly distinguish stating and using an existential without having a very verbose language. Okay, so same with u. So since u converges to x0 and delta is positive, we get n. And then, yeah, and then the same, since we've got, and then I'm repeating, so this, what is after this last since on line 59 is really the statement of h delta, but instead of saying by h delta applied to un, it suffices to prove, I'm just recalling what h delta is saying. So I'm not saying that this second version is better or worse than the first one. This is a choice that you get as a teacher using this library, whether you want to use one style or the other. You probably don't want to mix both styles, because if you do that, it means there are many different syntactical variations that students need to keep in mind. This is a difficulty for any tactic language, whether or not you're teaching. There is this tension between providing flexibility by having many tactics, so providing flexibility and expressivity, and keeping the mental load under control. So if you teach every variation, every syntactic variation, you can get very beautiful proof that read nice because there is less repetition and everything is smooth, but then you're putting a lot of constraint on the student's mind. One last, it's not really the last, but the last one I want to show variation is, you may have noticed that both, or all those proofs, except for the direct proof term, use backward reasoning, so reasoning by sufficient condition. You see, it suffices to prove. This is telling that I'm using backward reasoning. So let's do the same proof using only forward reasoning. So it's the same up to the almost the last line, so up to here. So here, instead of applying backward reasoning, I will apply forward reasoning. So switching the two steps around and saying, since we've got for all n bigger than capital N, absolute value un minus x0 is less than delta, and n is bigger than capital N, we gain, and then we get some new thing to work with. So this is also a choice that you can make as a teacher, whether or not you want to emphasize forward reasoning or backward reasoning, or discuss when to choose one over the other. So of course, when using a proof assistant, backward reasoning has an advantage because it allows the proof assistant to help you more. And I could explain that more in questions if you want, but this is a very well-known phenomenon. But many teachers on blackboards favor forward reasoning whenever possible, so you can use forward reasoning. Okay, so now something important to understand is that there are 3 levels of assistance for students. And this is important, especially if you don't have time to teach using Lean. If you're teaching, like I do, a full course about using a proof assistant and learning about proof, then you have a lot of time and you can tell students you should write all those words and be familiar with all the syntax. But if you're just doing this on the side, you've got just a normal math course and you want to use lean from time to time, or maybe as an optional component of your course, then it's a bit overwhelming to learn all this syntax. Because again, it is more complicated to write than the normal lean proof. What I call the normal lean proof is the tactic proof. I'm not referring to the proof term. This normal proof is easier to write, but it's harder to transfer to paper, both after writing the proof and transfer the skill to paper more generally. So there is this constraint that this is harder to write. So what can we do about that? So there are two levels of assistance. So three, if you count the hardcore mode. There is the assistance level, which is no assistance, just write the proof. And then you can use the help tactic. So using the help tactic would look like this. I type help, and then the computer answers with some suggestion. So it says you can start a proof by contradiction like this, or it also comments on the syntactic structure of the goal. So the goal starts with for all positive epsilon, hence a direct proof starts with fix a positive epsilon. So you can accept this suggestion by clicking this. And so of course, no, the next line makes no sense. And if you want to, you know you want to use HF, the continuity assumption on F, but you don't quite know how to do that because you forgot about this syntax of this by HF stuff. So you can type help HF, and again there are comments. So the first comment is about the unfolding the definition of f is continuous at x0, but it can also just see through the definition and suggest a next step, except that in this suggestion, you need to choose an epsilon 0. And here you can see this is not a safe step. You can see this is a step where you need to take some risk and commit to specializing HF to some real number and provide a proof that this real number is positive. Okay, so we can also do that, and so you can ask for help about the goal or help about how to use an assumption. And then, if this is not enough, and this is what I've been using in Orsay, so this help tactic, I've tested it with students. And in the beginning, I was worried that they would be clicking help, typing help all the time and without ever thinking, but this is not what I observed with students. It's rather more like I had to remind them from time to time that they could ask for help like this. But this is still in a context of a course where I have a lot of time and no constraints from my colleagues or anything like this. So in the Lean 4 version that has a lot more flexibility, because Lean 4 itself is a lot more flexible, I experimented with a point-and-click interface. So let's use this more assisted mode. So I can use shift-click to select sub-expression. So I will simply shift-click on the whole goal, and there are suggestions that appear. So there's a suggestion, the first one is to basically unfold the definition of convergence of a sequence. The second suggestion is to start a proof by contradiction, and the third suggestion is to just fix epsilon 0 right away. So let's click on the first suggestion, and then I click on the for all, and I choose to fix a positive epsilon, so the introduction rule. And then I will click on HF, which is the continuity assumption, click on epsilon, and here I've got three suggestions. I've got the suggestion to specialize HF to epsilon, or to epsilon over 2, or to epsilon plus 1. And so in that case, epsilon is okay. And I should say that here the computer is not checking that those numbers are all positive before making the suggestion. It will check, of course, after applying the suggestion, but this is not filtering out the bad ideas. In that case, there is no really bad idea. But okay, so I'll do that. And then the same with HU, and I try to go a bit quicker. Again, I can specialize to delta or delta over 2 or delta plus 1 because I selected HU and delta. And now I can instantiate my existential. So I click on the exist in the goal, and I click on N. And then again, I have two suggestions. Let's prove that N works or N plus 1 works. And if I had two natural numbers, I selected two natural numbers, it will also suggest trying with the maximum or the sum or the minimum or a number of suggestions like this. And this is all configurable by the teacher. And now let me finish this proof quickly. But the only important thing is I'm writing the exact same proof, but only clicking. So I will maybe say I will do the direct and forward reasoning proof. And something maybe interesting, I want to use H delta, and I will click on U and on N, and then we get the suggestion to conclude. Okay, so this is a full proof done only by clicking on stuff in the tactic state and accepting suggestions. So I'm not saying that every proof can be done fully by clicking, but at least in many cases you can do that. And now quickly, I want to finish with a version that shows more things from the library. So this is the squeeze theorem. So we've got three sequences of real numbers, U, V, W, and U and W converge to L, the same real number, and U is less than V, and V is less than W, then V also converges to L. So all the beginning of the proof is the same kind of things, yeah, up to here. So I get some capital N and capital N prime, and then I say the maximum of N and N prime works. And now there is something new happening. So this next line, it says, since N is more than maximum of N and N prime, we get N is more than capital N and N is more than capital N prime. And here it looks like the being more than the maximum is a conjunction, but of course it's not a conjunction on the nose. There is some lemma that has been applied implicitly, and I guess we could see what is the lemma that has been applied. No, it's weird. Okay, no, so the show term is not doing its job here. Let's not spend time on this. But it applied a lemma saying that being greater than the maximum is the same as being greater than both. And then again in the next line, it went silently from this inequality about absolute values to two inequalities. So again, silently applying a lemma saying that absolute value of x is less than y gives you that x is between minus y and y, without referring to the lemma name. And same here, and we want to prove, so this line is technically not necessary, but since it's been a while since we saw what is the current goal, it's just restating that what we need to prove now is absolute value of Vn minus L is less than epsilon. And again, there is something happening under the hood where we say, let's first prove minus epsilon is less than Vn minus L. So this is silently applying the converse of the lemma we silently applied in the previous line. And so we prove that. And then there is a calculation to prove that. So you can see minus epsilon is less than Un minus L by assumption. So this is familiar. The next line is slightly more interesting. So you go from Un minus L to Vn minus N, since Un is less than Vn. So there are two things that happened automatically here. So first, the H assumption was used and specialized to N, the N that is fixed here, this free N. And also, silently, there was a lemma applied saying that if A is less than B, then A minus C is less than B minus C. Okay, because this minus L has been ignored by the justification that is here. So this is obviously under the hood using the G-Conger tactic by Carnero and Macbeth, and in addition to all the Mathlib tactics, and the other inequality is similar. So here it uses, in this new example, it applies lemmas without naming them, and also it just justifies inequalities by again applying lemmas without naming them. So all this you can configure as a teacher. So you've got lots of choices if you want to use this library. You've got lots of choices to make. You can decide which proof style you want to teach. You can decide the help level, so whether you teach the help tactic, whether you teach the clicking. You can also, of course, deactivate those things, the help tactic and the clicking and stuff to get suggestion. And you can also decide what are the anonymous lemmas, so what are the lemmas that will be automatically applied. And if I go to this etcdemo.lib, you can see, so there are definition of continuity and limits of sequence and with some notations, but also you see configure unfoldable defs. So those two definitions are marked as being unfoldable in the sense that when we started the proof here, the help command suggested to unfold this definition of converges to because it was marked as unfoldable here. Because if this is not opt-in, then the lean will happily suggest to unfold the definition of real numbers, and you will really get in trouble. Or even unfolding the definition of addition of natural numbers would already bring you down the natural number game rabbit hole. And the anonymous fact splitting lemmas are configured here. So you can see that this absolute value of A less than B implies minus B less than A and A less than B has been marked as an anonymous fact splitting lemma. So you can configure that. And the goal splitting lemmas are also configured, and logic intro is a set of lemmas that are, if I click on it, you can see this is if and only if intro and the prime version and intro and so on. You can define a list of lemmas and configure all that. The data providers are also configured. So the reason why the suggestion was to apply specialized to epsilon or epsilon over 2 and so on in the widget thing, so in the interactive click point and click proof, you can see that for real numbers, it will suggest the number you clicked, so this is make self, suggest it will use make half, so it will suggest dividing by 2, and the numbers default is add 1, min, max, and add. So this is all things you can configure, and this is very easy to write even if you are not comfortable with programming in Lean. And if you are comfortable with programming in Lean, you can also configure the suggestion providers so that react to selecting stuff in the info view. But this time you really need to know programming in Lean. So I'm just showing you this so that you can see the difference between what I call things requiring programming in Lean expertise and things not requiring such expertise. I know I'm out of time. I'm just concluding.
Okay.
You can also choose your language. So, of course, I cannot use what you just saw with my students because French undergrads cannot read any English. So, if we want to teach that in France, you need it to be in French. And so, okay, it's rebuilding stuff, but so it should be also highlighted. So there is a French version, and if you want to translate it into another language, there are explanations about how to do that in the library website and on the paper, but I don't have time to explain that. So this is what I wanted to say today.
Thank you so much. Can we just thank Athina and Patrick for their talks? We will have a chance now for questions and any discussion. I just want to say for people who do want to take a quick break, our next set of talk starts at 1:15, so do take the opportunity to do that. But either in the room or online, unmute online or just drop a question into the chat or Q&A box. Is there anything that people would like to ask, would like to comment on? From my point of view, Athina, when you were talking about the two different strategies that these students had, the one that was essentially trying all sorts of things, getting instant feedback and realizing that the tactic didn't work and they needed to refine their approach. Maybe the sample size is too small, but it strikes me that maybe such students would find it more difficult to transfer that to paper, because they're relying on this immediate feedback loop. I don't know, is that something you saw?
So you're right in terms of we cannot really make huge assumptions, but we have a lot of data from those 4 students. So from what I've seen from the student who was essentially just trialing something, this is not, it's not something that I haven't seen with other students. So when I was present in those Thursday sessions in the first study that I've mentioned, a lot of students were trialing, trying to get kind of familiar with what what Lean does. So I think it is expected initially to have this kind of trial. And I think what is very different is if the student is already aware of how they want to approach this proof on pen and paper. So the ones that would do like a diagram or would think about, okay, what do I need to do? And then try to see how I can do this in Lean. Those would be, it will be easier, as you said, to kind of transfer things that they've learned in Lean to then pen and paper proof. But the ones that had an idea and they were also familiar with the vocabulary and the syntax, which happened for this student as well later on, then we see a very different way of engaging.
Thank you very much.
No worries.
And there's a couple of questions in the chat. Let's take the one for Patrick first. From Alvaro, have you found any language barriers when trying to develop verbose Lean? It might be that modern languages are sometimes too limited to describe what Lean is doing.
I'm not sure I understood this question. Can you say that again?
So it's in the chat, but were there any particular language barriers you found when trying to develop verbose Lean? Difficulty translating, say, the Lean tactic into, or the Lean proof term into the relevant natural language, controlled language form.
There are some. I mean, of course, if you look at the example with the direct proof term, I mean, it's hard to say that in one sentence, okay?
Right.
But this is not what I was trying to do. And I showed that because just to remind you that this is what Lean is checking under the hood. So all the proofs I've shown are building this proof term. And so, of course, the natural language, and when I say natural language, of course, it's always an abbreviation for mathematical natural language. And I'm not about discussions you have by drinking coffee, but so the mathematical natural language is not flexible enough to express that in one sentence. But for the proof steps at the level of detail that I wanted for, again, this is all targeting first-year undergrad students. I had no issue at all. In the Lean 3 version, English was trickier because there were more collisions with the Lean language keywords, like let is a keyword in Lean 3, and soit, which is the French version, is not a keyword.
Okay.
So that was, but this was all in Lean 3 with the Lean 4 flexibility. This is not an issue at all.
Okay.
So I guess the answer is no language barrier.
Okay, thank you. And Athina, I think you've answered that question in the chat, but maybe you just want to say something as well.
Not fully. So I answered the first bit, Evgenia, and then I think the kind of the other aspects that you're highlighting, Evgenia, in terms of your question, is whether it is a huge barrier. So for that one student, this was a barrier, but this is very clearly indicated in the text of that particular level. and the student was aware of it, and they said afterwards that even like I was aware of it, but still was very difficult to not visualize them. But the other 3 students didn't actually have this kind of difficulty in that level or the other levels as well. So I would say with kind of highlighting it appropriately, it doesn't need to kind of be dressed in a particular manner, if that makes sense.
Okay.
I don't know what is the current status, but in Lean 3, we definitely had a tactic asking to put parentheses everywhere. I don't know if it was ported to Lean 4, but this is not hard to do. I mean, I had that in the Lean 3 version of the library. I should check the status. And it's also,
Kyle wrote it, right?
Hmm?
I think Kyle wrote it, and one problem was that it would put brackets around everything.
Yeah.
So it's like open brackets A plus, open brackets B plus C.
Yeah.
No, that's too many. I want just the right amount.
And also it's already since the late days of Lean 3, the fact that the tactic view is highlighting stuff when you move your mouse, like what I'm doing here, it helps a lot to understand how things are grouped together. So this is something you need to teach students early. So it's not such a big issue in my.
Yes. Thank you. And just one last opportunity for any more questions from the room or online, or the discussion points.
I forgot to say something. I saw in the chat, Jim. So just in case this is Jim Portuguese, I didn't say it a lot, but it's in the README of the project. If you would rather use Coq instead of Lean, you should check out the Coq Waterproof project that has lots of common goals and also some of the common solutions compared to the library I was showing. And also, one last link that I wanted to mention is that we do have a grant from the French research agency that is called APAM. So it's all in French, but it's the aim is to assess whether this is really helping students. And the big boss is Cécile Ouvrier-Buffet, who knows how to assess this. And instead of what I'm doing myself, is just feeling that students become better, but this is, of course, very limited assessment. So hopefully in the future, we will have rigorous data about whether this is doing any good. I mean, not only the Verbose Lean library or other proof assistant uses.
This is new news. I didn't know about this.
Yeah, this is just getting started, and it's
I think
actually started in January, but we needed to set up the experiment and stuff. So the next year will be the actual experimentations.
Cecile and quite a few colleagues were at the TEDU conference at
Sure.
the start of the month. So we met and discussed. It was really nice to hear that this is happening.
Excellent. Well, thank you. Thank you again, Athina, Patrick. We'll just break for 5 minutes. If Heather can check whether you can share your screen, etc., and Kevin will also get you ready to when you will talk. Thank you so much.